Right. So, I promised last time that we would talk about a multidimensional Langevin equation for a particle in a magnetic field, and then I will talk about the properties of the Wiener process itself, namely Brownian motion itself. But before that, just to complete what I was saying the last time, if you looked at a Brownian oscillator, a particle moving on the x axis bound harmonically to the origin by this potential, the spring force minus half whatever omega naught squared minus omega naught squared x, then we wrote down the phase space distribution. We wrote down a differential equation for the phase space distribution, joint distribution in both x and v, the conditional density in both these variables. And then I said you can solve this, you get a bivariate Gaussian in x and v, and if you integrate over x you would end up with the distribution in v, if you integrate over v you would end up with the distribution in x. We also saw that if you have the overdamped oscillator, namely the one for which gamma is much bigger than omega naught, the free frequency, then it turns out that the position itself satisfies a Langevin type equation and you get a solution similar to the Ornstein-Uhlenbeck solution, except that the relaxation time is not gamma inverse but omega naught squared over gamma the whole inverse, right. So it turns out that V relaxes on a time scale 1 over gamma, but x for the oscillator, for the Brownian, for the Brownian oscillator, x relaxes on a time scale which is gamma over omega naught squared. Okay. We saw this from the overdamped oscillators thing. The fact that this is an Ornstein-Uhlenbeck process and so is this an Ornstein-Uhlenbeck process is responsible for the statement in many books that the Ornstein-Uhlenbeck process itself is called the oscillator process. What they mean is that it is the position of the harmonic oscillator when you have the overdamped case. Okay. Now it is immediately clear from this that in the overdamped case gamma over omega naught squared is much bigger than 1 over gamma, which is exactly what overdamping means. Gamma is much bigger than omega naught. Okay. So the velocity thermalizes, if you like, much more rapidly than the position does. It is much more sluggish, but there is no long range diffusion in this problem. Both x and v go to equilibrium distributions which are given by the equipartition theorem, if you like, in statistical mechanics. Okay. So much for this. Now for a multidimensional motion, 3-dimensional motion for example of a Langevin particle, if the particle is free then you would end up with an equation which says v dot, now it is a vector. So let me put a wiggle underneath to show that it is a vector. This is equal to minus gamma times v plus square root of gamma over m, a vector valued force eta, noise eta here, and this is the free particle Langevin equation where each of these is a 3-dimensional vector. So v for example has components vj, j equal to 1, 2, 3, and this guy also has components eta j running over 1, 2, 3, and it is a 3-dimensional delta correlated stationary Gaussian white noise, which means that this satisfies an equation of the form eta j of t equal to 0 for every j, and moreover eta j I of t eta j of t prime equal to a delta function ij delta of t minus p prime. So the different Cartesian components of this noise are uncorrelated to each other immediately. Now once you have that information, by the way, you can solve once again, you can solve for the Langevin equation, solve for the velocity and find all its properties from those of eta, or you could write down an equivalent 3-dimensional Fokker-Planck equation for V and solve this equation to get a generalized Gaussian solution. it will be the 3-dimensional analog of the Ornstein-Uhlenbeck process. Okay. Now we know that that process is exponentially correlated. We know the velocity correlation time is gamma inverse. Okay. So we could ask what is the correlation between different components of the velocity, okay. And we can do that in many ways. We can solve this for V and then compute the velocity autocorrelation function, but we already know from the one-dimensional example, we saw that in that case V was a stationary process and V of 0, V of t was equal to k Boltzmann t over m e to the minus gamma mod t. This is what we had for a single component here. Now it is possible to get this equation directly, get this solution directly. If you know that V is a stationary process, we can do this by a very cheap trick, and that is to simply write the Langevin equation down. So let us do that. So I have V dot equal to minus gamma V plus root gamma over m 8 of t in the one-dimensional case, and this is a function of t. So this is V dot of t equal to V of t plus eta of t. And I want to find out what is V of 0, V of t in this case. So what I do is to multiply both sides by V of 0 on the left hand side and then average. So V of 0, V of t, V dot of t average equal to minus gamma V of 0, V of t plus root gamma over m, the average value of V of 0 with eta of t. Okay. And what do you think this average is? What is the correlation between the velocity at time 0 and the force at t greater than or equal to 0? By causality, you would expect that the force at a later time does not affect the velocity, the output variable at an earlier time. That is causality, right. So this is actually 0, this quantity is 0. Now you might say, aha, what about equal times? What about at t equal to 0? So at equal times, what do you think this correlation would be? V of t, eta of t. What do you think this is going to be? That is a more delicate question, but again I argue the same way. Eta of t by from this equation here controls the acceleration. So the acceleration is determined by the force, not the value of the velocity. This is like an initial condition for this force at equal times, right. So again it is completely uncorrelated to each other. So that is 0 as well. So causality says this quantity is 0. That is a principle we have not yet invoked, okay. It says that the cause cannot precede, the effect cannot precede the cause, it is not anticipatory, right. Because of that, you can make set this equal to 0 and this is some function of t, but then d over dt V of 0, V of t is precisely this quantity. There is no time argument here at all, or if you like put a t0 here and a t0 plus t here and it is independent of t0, and the time derivative with respect to t acts only on this thing here, and it is therefore equal to the time derivative of the correlation function, and this is equal to minus gamma, the same thing. Okay. Which immediately says that this should be equal to, therefore V of 0, V of t should be equal to V of 0 if you like squared, squared inside V squared of 0, that is the initial value, e to the minus gamma modulus t, because we have written this equation for t greater than 0. Okay. And this now, this quantity is now determined from equilibrium. The fact that in stationary in equilibrium in the Maxwellian distribution, this quantity is just kT over m, right. So this immediately tells you So even without explicitly solving the Langevin equation, you can actually find what the correlation function is. Okay. What do you think is going to happen there if I did the same thing? Well, I write this out for each Cartesian component and notice exactly the same property as before. I multiply this for Vj, I write Vj dot is a Vj here and an eta j, and I multiply by Vj of 0 on the left hand side and solve the differential equation, use the same causality argument, and you get exactly the same answer for each Cartesian component, right. So therefore, what would this be? As a vector, V of 0 dotted with V of t in equilibrium, what would this turn out to be? Yeah, it is kT over m times e to the minus gamma t for each of these components, and then you are taking a dot product, so this is equal to 3. What would this be? What would V of 0 cross product V of t be? Okay. So now I want correlations of V1 with V2, V1 at an earlier time, V2 at a later time, and so on, unequal components. What do you think is going to happen? So I write the ith component of this as epsilon ijk, vj and vk out here, and I do the same trick as before and again compute, I can solve for this thing. What do you think it will be? It will turn out to be 0 because the different Cartesian components are completely uncorrelated with each other because they are driven by noises which are uncorrelated with each other. This property here, there is a delta function here. So the correlation of one component of eta with another component of eta even at the same time is 0. Okay. So this is identically 0. Okay. What would happen if I switched on a magnetic field? What is going to be the equation of motion? Yes, because now we have exactly the same Langevin equation as before, but now there is a term, let us say the charge of the particle is q or something like that, plus q over m v cross b. So there is this term plus root gamma over m 8 of t, that is not affected as before. Now all kinds of correlations will happen because it is clear that this velocity dependent force, the acceleration in the x direction depends on the velocity in the y direction and so on and so forth. So there is correlations between the different components. Even though this noise is uncorrelated, the Cartesian components are uncorrelated, because of this term here you are going to get correlations between the different velocities. And you can solve this problem for a constant magnetic field exactly the same way as before. Once again we know from physical arguments that the energy of the particle is not changed in a magnetic field, that the Maxwellian distribution is not disturbed at all in equilibrium. There is a stationary distribution, that is the Maxwellian distribution. All that will happen is that the diffusion coefficients in the different directions are going to be different, because in the direction of the magnetic field it will be the unperturbed one, but in the direction of the field there will be this cyclotron motion inhibiting long range diffusion by changing the diffusion coefficient. Nothing else is going to happen. So I leave you to compute these quantities in this case here. So in the presence of B. It is a simple exercise but a very instructive one. You can find out what are the cross correlations in this case. Okay. This is a very special kind of force here. It is velocity dependent, but it is linear in V once again, and this drift of course is linear in V. Now we know that anything that is linear in the variable, you can solve the problem completely. You can write the Fokker-Planck equation down and solve it. You can find the Green function, you can solve the differential equation, the Langevin equation itself, etc. So in exactly the same way you can extend whatever we did earlier in the absence of a magnetic field to this case here. We already also saw what happens in the case of the oscillator, where you have a term that is linear, but that is linear in x instead of v, and that did not bother us either. We were able to solve it. So this problem can be explicitly solved. You can look at it exactly. In fact, as the particle does cyclotron motion with a characteristic frequency, what is the characteristic frequency for this cyclotron motion in a magnetic field B? There is a quantity of dimensions. Once you have a thing like this, what is the cyclotron frequency? Where the force is q over m v cross b, right? So there is a time scale here, this is v dot, so there is a 1 over t here times the velocity, there is a velocity here already. So it is clear that whatever is of inverse time scale must be q b over m, right? So that is the cyclotron frequency, okay, just from dimensional arguments. Turns out to be exactly that, the numerical factor is 1. So if you go to a rotating frame of reference, which is rotating about the direction of the magnetic field with this frequency, then it is as if you do not have this field. So in that frame, so you must transform from V to a variable u which takes into account that rotation, and then of course you can solve the Fokker-Planck equation much more easily, or you can leave it as it is and work it out including this V. Okay. So I leave this computing these quantity correlations as an exercise. Okay. Now let us get back and examine this Brownian motion itself a little more carefully. We have to define what is meant by Brownian motion. And by this I now do not mean the physical Brownian motion, which was what was discovered first when they had these Robert Brown observed among other people. He first understood what the nature of this motion was to some extent when you crush pollen grains and put it in water, and then you look at it under a microscope, you see these irregular jagged motions, jerky motion of these particles, and that is what Brown described, and it was called Brownian motion. Okay. That is physical Brownian motion. We know what it is due to, we know that it is due to molecular collisions and so on. But mathematical Brownian motion is an idealization. Okay. This is defined by in several ways, and I am going to define it in one particular way today, but this is exactly what the x which occurs in the diffusion equation, the simple diffusion equation, is supposed to describe. So the process x whose probability density obeys the ordinary diffusion equation in any number of dimensions is called mathematical Brownian motion. And let us go back and ask what that diffusion equation was. So you had delta p of xt over delta t equal to d2p over dx2 in one dimension. Otherwise you got a del squared out here, okay, with some given constant d. Okay. And we know this comes from the Langevin equation for a free particle in one dimension in the presence of this random force eta in the diffusion limit, in the limit in which t is much bigger than gamma inverse. Okay. And we also saw that this d is related to that gamma by kt over m gamma was equal to this d. Right now we are not worried about it, we just ask what does this say, what does this equation say. Okay. And it is useful to write down its fundamental solution of this particular equation. The solution which says that p and its derivatives vanish at plus minus infinity in x. and we assume also that the particle starts at the origin at t equal to 0. Okay. So, you are really solving for the green function of this differential operator. So, the fundamental solution is p of x comma t. The normalized solution is square root of 4 pi dt e to the minus x squared over 4 dt. Okay. That was the basic solution. Now, of course, you started this process at some time t prime, then t gets replaced by t minus t prime, and if you start at some point x naught, then x gets replaced by x minus x naught. Okay. Now we ask, what is the stochastic differential equation corresponding satisfied by x corresponding to this equation? We have this correspondence between diffusion processes, Fokker-Planck like equations, and stochastic differential equations, which we call the Langevin equation, right. So, by that correspondence, this thing here is entirely equivalent to saying x dot equal to square root of 2d times eta of t, where this is a Gaussian white noise. By that I mean eta equal to 0 and eta of t prime equal to a delta function. Okay. Okay. So, this process x, I have not distinguished here for ease of writing between the random variable itself and the values it takes, which is what appears here in this thing here. Okay. This is a matter of notation, one should be a little careful, but no confusion should arise from this. So, this process x is the integral of white noise, if you like, because you could write x of t equal to an integral from 0 to t dt1 eta of t1. Formally one can write it in this fashion. For particles which start from the origin at t equal to 0, this is the formal solution to this equation. Is this a stationary process? That is a stationary process. Its statistical properties are independent of the origin of time, but this is not. Remember, the velocity was a stationary process. When I wrote the Langevin equation down, it turned out to be a stationary random process. This one is not a stationary random process here, and that is easily seen because all you have to do is to look at x of t prime and take its average. Now, this average we are now taking for all those particles which start at 0 at the origin at t equal to 0, right. So, it is a conditional average. There is no equilibrium distribution corresponding to this because this guy vanishes as t tends to infinity. There is no stationary distribution at all for this process here, unlike the velocity process where you got the Maxwellian as the stationary distribution. Now, what is this going to be? So, let me denote by this overhead bar this conditional average, that it is for particles which start at t equal to 0 at x equal to 0. Okay. So, what is this guy going to be equal to? It is equal to integral 0 to t dt1, 0 to t dt2, t prime dt2, and then eta of t1, eta of t2 average. Whether I put this average or I put angular brackets here does not matter, because our philosophy is that the random noise which comes from all the other particles is not affected by the motion of this single test particle. Okay. So, that acts like some kind of heat bath or reservoir and affects the particle we are looking at, the tagged particle, but there is no effect of the tagged particle on the noise itself. Okay. All we have to do is to put this in here, and then you immediately see that if you integrate over T1 and T2, and T2 is up to T prime and T1 is up to some number T, the integration has support over this 45-degree line. Therefore, it gives a non-zero contribution only as long as T1 runs up to T prime, and after that it is 0. And if it runs up to T prime, you can get rid of the delta function integral, delta function to get rid of the T2 integration, and then T1 runs from 0 to T prime, right. And had it been the other way about, had T prime been bigger than T, what I have shown here is T prime less than T, it would run up to the lesser of the two always. So this immediately is equal to, oh there is a 2D also, 2D equal to 2D, the lesser of T and T prime. Okay. So that is the point. It is not stationary. This is not a function of T minus T prime as you would expect. Had this been stationary, you would have ended up with T minus T prime. It is not true. Okay. However, the increments are stationary because eta itself is stationary. Therefore, I could write this as dx, if you like, the increment in x is eta of t dt. And then those increments are stationary because eta is stationary, right. Or another way of saying it is, if I computed x of t minus x of 0 and x of t prime minus x of 0 and took the average over that, you would end up with 2t modulus of t minus t prime. Okay. So this thing here is a very crucial result. This is a very crucial result. In fact, you could say that if you have a process whose average is 0 and whose correlation, autocorrelation satisfies this thing here, and you are given that it is a Gaussian process, if you are given that, then all the other properties of Brownian motion follow, including the fact that it is a Markov process. Everything else follows. So that is one way of defining mathematical Brownian motion, namely it is a Gaussian process whose mean is 0, x of t average is 0 at any time t, and whose autocorrelation is this function here, some constant times the lesser of t and t prime. Okay. And this suffices to define the process, and it has got remarkable properties. But you already see that x is smoother in some sense than this white noise, because it is the integral of white noise, but it is going to be rough, as we will see, as it is bad enough as it stands. It is very different from what the velocity was. That was the Ornstein-Uhlenbeck process, and that had an autocorrelation which was exponentially dying down. Okay. This looks very different altogether, and it is non-stationary as it stands. Now some statements about the paths, the possible trajectories, if you like, in a typical realization of this x of t, and I am not going to prove this. This requires now a little more mathematical machinery, which I am not going to use here, but here are some facts. So let us call it a Brownian trail. If I plotted, here is t, and I plotted this process x of t, Brownian motion, then a lot of interesting facts emerge. In a typical realization, it is hard to plot. By the way, there is no way that I can actually draw a realistic realization. But if I started here and did this, went like this, then the statement is that this x does not have any bound. In any short interval, however short of time, you can attain arbitrarily large values of x on either side of the axis. Okay. The second property is that while it is continuous, the curve is continuous, it is not differentiable anywhere, in the sense that this is a very singular object. This guy is a very peculiar singular object, okay. Although we have written it in this fashion, it is really a very singular object. This curve is kinky on all time scales, doesn't have a derivative almost everywhere. What should it be in order for it to have a derivative? It is clear that you must have x of t plus epsilon minus x of t, the modulus of this guy here must be of order epsilon, so that if I divide over epsilon and take the limit, I have a finite number, right. But it turns out that this is less than equal to some constant times epsilon, taking epsilon to be positive, to the power beta, where beta is less than half. The fact that you have a positive beta shows that the curve is continuous, and it is said to be Holder continuous with exponent beta if this is satisfied. Okay. But it turns out that beta is less than half almost everywhere, but it can be made arbitrarily close to half from below almost everywhere. Okay. So this quantity beta tends to half from below. There is a set of points where beta is exactly a half, but that is a set of measure 0. On the other hand, beta can become arbitrarily close to half from below. Okay. So it is almost certainly not differentiable, because you need beta equal to 1 for differentiability, and this is less than that. Okay. So that is the first property. The other property, the next property, is that these points where it crosses the origin, they form the 0 set of Brownian motion. So you start from 0 and you ask when does the particle come back to 0, etc. This 0 set, the set of points such that x of t is equal to 0, has a fractal dimension which is half in this case. That set is not countable, and its box counting or fractal dimension happens to be half. This is a reflection of the fact that in this Brownian motion x squared, the square of the length scales like the time to first power. That property appears over and over again in this business. You could also ask, suppose you start at 0 and it moves up to the positive side rather than the negative side, in a given time interval, what is the fraction of the time that it spends without crossing? Okay. You can ask for the distribution of that fraction. Okay. So let us suppose that in a time interval t, what is the statistics, what is the distribution of the fraction? Let us suppose that in a given time interval t here, and this is 0, we could ask for the fraction of the time, let us call that t plus over t, that it spends in the positive side without crossing 0, or negative side by symmetry. Okay. So now this fraction here has an interesting distribution. It must have a probability density function first of all, and it turns out that that density function, let me call it f, the PDF of this random variable for a given t, that is a random variable t plus, this PDF f of t plus, normalized PDF, when you integrate this from 0 to t you must get 1 of course. So this is equal to 1 over okay, and that can be rigorously established. What does that graph look like? What would this look like? Well, it becomes unbounded at both 0 as well as, so t plus is sitting here. Yeah, it looks like an inverted U of some kind with some mean value at half. T over 2, okay. But that is the least probable, that is the least probable value. You would normally expect that in a given time interval t, the fraction of the time, the probability density function of the fraction of the time it spends on either the positive side or on the negative side of the x-axis is the most probable value you would think is a half, but it is the least probable value, okay. So it is clear that most of the time this guy is spending this particle is spending its time either on the positive side or on the negative side of the axis, and yet in any finite interval of time it crosses this axis an arbitrary number of times, okay. So it is a very weird kind of motion. The cumulative distribution function 0 to some number t plus dt plus prime f of t plus prime is the actual distribution function of this fraction, and when t plus is equal to t it should be equal to 1, right. This is equal to sine inverse t plus over t, and sine inverse 1 is pi over 2, so this is 2 over pi. Okay. That is easy to derive from here, you complete the square and integrate, that is it. This is called Levy's There is an even more exotic law which says where is this particle likely to be most of the time, okay. And it turns out that if you plotted time against the following function, it starts at the origin. So if you plotted this function 2t 2 dt, well let me 2 d dt, let us work in dimensionless units, put d equal to 1, 2t log 1 over t square root, plot this function for sufficiently small t, for t less than 1 this guy is positive, goes up there, and this is minus that function, this guy is minus square root of the same thing. And you multiply this by 1 plus epsilon, you would get a curve like that, and this is 1 minus epsilon and the square root, and this function is 1 plus epsilon times this square root. Okay. Then the particle is almost surely going to be in this range, either there or here, almost surely, for every t, sufficiently small t, okay. And for sufficiently large t, the 1 over t in the log is replaced by t, okay. So look at what is happening. I mean, we sort of know that the mean square, root mean square displacement is proportional to square root of t. The mean square displacement proportional to t, so the root mean square is proportional to root of t. So we kind of know there is a square root of t, which is sitting here. that will be like the mean square displacement. But now we are making a statement about the path itself, these points. This is called the law of the iterated logarithm. It is Khinchin's law. And it is characteristic of Brownian motion. So, all these properties and more emerge from the very simple fact that we define mathematical Brownian motion as a Gaussian process with 0 mean and with correlation which look like this, x of t prime, correlation is the lesser of t and t prime. Okay. Now you could ask, is there any relation between this process and the Ornstein-Uhlenbeck process? Because in some sense we said, look, the Ornstein-Uhlenbeck process came about, has an exponential correlation, and it came about when we treated the motion of this Langevin, this Brownian particle a little more carefully, keeping track of the velocity correlation time and so on. We also said that that process is exponentially correlated, and I made a statement that the only continuous stationary one-dimensional continuous stationary Gaussian Markov process is the Ornstein-Uhlenbeck process, and it has an exponential correlation, right. I made that statement. So in that sense, that is a fundamental Gauss Markov process. This is Gauss and this is Markov, it is not stationary though. Is there a connection between this and that? And the answer turns out to be very interesting. It turns out that every Gaussian Markov process, continuous Gaussian Markov, continuous of course because it is Gaussian Markov process, is some kind of Brownian motion of some kind. So let me call this Brownian motion, mathematical Brownian motion, this quantity dw. So let us put this 2d, let us get rid of that 2d, and let me call w of t a process such that w dot of t is eta of t. So I do not have these constants to fool around with, or if you like w of t, dw of t is eta of t dt. This quantity, this w of t is called a Wiener process or mathematical Brownian motion, and it satisfies w of t prime average equal to the lesser of t and t prime, and w of t average equal to 0. It is a Gaussian process which has got 0 mean and whose autocorrelation is given by this quantity here. Okay. In loose terms, it is the integral of white noise, okay, and it is a process with stationary increments because this guy is stationary, okay, and that is an increment in the process. Okay. Now, what I was going to say was, lost my train of thought. Yes, now the statement is that every Gaussian Markov process, okay, it has to be Markov, it has to be Gaussian, is some kind of Brownian motion, a Wiener process in rescaled variables. So if you give me an arbitrary Gaussian Markov process, let us call that process I of t, in distribution, as far as the probability distributions of this process are concerned, this thing would be equal in distribution. So let me write a d here to show that the probability distributions are the same, can be written as some Wiener process in some rescaled time times some other function of t. So this is an arbitrary Gauss Markov and you can always write it as a Brownian motion in some other variable. Okay. We will see an explicit illustration of it. I want to connect up the velocity process, the Ornstein-Uhlenbeck process, to Brownian motion of this kind. Now you might wonder how that is going to happen. After all, this fellow here has a correlation which is very different. It is not a function of t minus t prime, and yet this fellow here, if it is the Ornstein-Uhlenbeck, is a function of t minus t prime, right. How does this happen? Well, the mapping is as follows. You can kind of guess what the mapping is going to be. Let us recall what the velocity process did. So we had a v of t such that the average value of v of t for a given initial condition was equal to v naught e to the minus gamma t, if you recall from the Langevin equation, and we found that the correlation time, so if I define delta v of t equal to v of t minus v of t bar, subtract out this average, conditional average here, then delta v of t, delta v of t prime, this quantity conditional average, we discovered this guy here was equal to k Boltzmann t over m e to the minus gamma mod t minus t prime. This is what we discovered, right. This is what we saw from the Langevin equation, and it follows from either the Langevin equation directly or from the solution to the Fokker-Planck equation. Okay. Agreed? Okay. Now, how is this going to be related to that? Well, the claim is the following: delta v of t is equal in distribution apart from this constant. So let us get rid of it by writing square root of kbt over m. This guy is t minus t prime if t is greater than t prime, and t prime minus t if t is less than t prime, right. So let us write this as equal to e to the minus gamma t, a Wiener process of e to the twice gamma t. So this scale factor outside is e to the minus gamma t, and the time is getting replaced by e to the t. Okay. Then we apply this rule. So it immediately follows, this thing will immediately follow that delta v of t, delta v of t prime average is k Boltzmann t over m e to the minus gamma into t plus t prime, these two factors, and then the smaller of e to the 2 gamma t, e to the 2 gamma t prime. Okay. Of course, this is a monotonically increasing function of t. So if t is bigger than t prime, it is this guy, and that immediately kills this factor and makes it a plus sign. So you end up with this result here. So this is how magically this exponents, where the exponents add up, it immediately, once you take the exponents, right, e to the t instead of t or e to the 2 gamma t, immediately this correlation looks like this, but in a rescaled variable. Okay. So you could say that Brownian motion is the Ornstein-Uhlenbeck process in logarithmic time, if you like, or the Wiener process in exponential time gives you the Ornstein-Uhlenbeck process. Okay. But the statement is every Gaussian Markov process can be converted to Brownian motion. So you could now ask, what about the sample paths of the velocity process itself? What would those look like? After all, the X process had this very jagged property, and I said it is a fractal, it has got 0 sets and so on, which are fractals and not differentiable. What would happen to the V process? Well, the crude answer is whenever you have this kind of white noise somewhere in there, you are going to see this weird property. always. Whenever there is some driving force which is a Wiener process, you are going to have which is the derivative of a Wiener process, you are going to have this problem always of this very irregular paths. Okay. So even for the velocity process that is still true, but it is really smoothed out in many other ways because of this finite correlation time and so on. Okay. Now you could ask what happens in other dimensions, higher dimensions and so on. So that the next thing we are going to talk about is a kind of generalization. I already mentioned there is a connection between these diffusion processes and the Fokker-Planck equation here. We would now like to go backwards and ask what about the Fokker-Planck equations obeyed by other random variables connected to Brownian motion. For instance, here is one. If you have diffusion in d dimensions, right. So you have a probability density which satisfies the diffusion equation in d dimensions. So it is like a whole lot of Brownian motions in higher dimensions, right. What sort of properties do those trails have? That is one question. The other question is what kind of Fokker-Planck or stochastic differential equation is satisfied by other functions of these variables which are Brownian motion. For instance, in 2 dimensions if you had x and y, you could ask what about the random variable x squared plus y squared, what kind of distribution will that have, what about its probability density function and so on, what kind of Langevin equation would that satisfy. So what we will do is to write down from the original diffusion equation, we write down what the solution is or what the Fokker-Planck equation is, corresponding diffusion equation is for these random variables, and then use this connection between the stochastic differential equation and the master equation in reverse to write down the stochastic differential equations and see what the new information we get. And that is an interesting exercise. So one of them would be to ask if I call this equal to r squared, what about the diffusion equation satisfied by r squared, what about the Langevin equation satisfied by r squared, okay. How does that look, what are its features and so on. You could also ask what about r, what about r itself, r squared, these are different random variables if you like. What about the square of a Brownian motion, what about the nth power of Brownian motion in one dimension, say what about x squared or x cubed or x to the n, what does that look like, what about e to the x, what does that look like and so on. We will talk about that. E to the x is a very weird property, it is also a kind of Brownian motion, it is called geometric Brownian motion, and that is the one that is used in the analysis of these financial markets. So this famous Black-Scholes equation which you have, which people use in and stochastic differential equations as applied to stock market prices, is essentially geometric Brownian motion, also called exponential Brownian motion. So we will try to write down the stochastic equations for that and see what their properties are. Well, some properties will become, they are not so intuitively obvious. For instance, if you ask in 2 dimensions, for instance, if you say okay, the particle is moving on this plane, what kind of trail does it have? It turns out that this particle also has a probability 1 of returning to the starting point, whatever it be, in other words intersecting itself arbitrarily an arbitrary number of times. In fact, the trail if you wait long enough will fill the plane, it is space filling, it has a fractal dimension of 2, almost every point is visited an infinite number of times, revisited an infinite number of times. That is one of the properties. And you could also ask is it completely unbiased? It is, because it says the x and y directions, these motions are not correlated to each other at all, but if you write it in terms of the radial variable, then you see there is going to be a bias immediately, because it says that although there is no drift term when you write the Langevin equation in the Cartesian components, if I now look at it at some point here, at some instant of time, right, and ask what about the radial variable, what is that going to do, then you see without loss of generality we will take that point here just for ease of illustration. Anything that pushes it outside this circle is going to increase the radial distance, anything inside is going to decrease it, right. Now assuming that you have equal kicks in both the x and y directions in an unbiased way in arbitrary directions. If you say in a given kick it can't go further than that, although that is not true, it can go arbitrarily far, you immediately realize that if all these points are equally probable, the measure of this set is bigger than the measure of that set. So you now realize that the tendency will be to increase R rather than decrease it. There is more tendency to increase R, and of course as you get close to the origin, if you are at the origin, then any perturbation is going to increase R automatically, but it is true at every point in this fashion. So this means that when you write the stochastic differential equation for R, in addition to the diffusion term there will be a drift term as well, and it is a real effect. So we need to see what that term looks like. Intuitively I would expect that the closer you are to the origin, the greater this drift will be, so I expect it will go like 1 over R maybe or something like that. You will see that it indeed is so, and it will also be dimension dependent clearly. So for every d greater than or equal to 2, this effect is going to show up, and we will write this down, these equations down and look at it. So we will do that next time.